Good morning. Yesterday we learned a lot about the theoretical processes behind X-ray diffraction, and we also learned how to identify phases with Profex or with other software. And with this, we now have everything we need to actually perform a Rietveld refinement. And I mentioned it yesterday a few times that the actual refinement is not performed by Profex, but by a Rietveld refinement kernel, a separate program that is called BGMN. And we can use BGMN without Profex. So we would call a command on the command prompt and run the refinement. That's it. So the refinement has been performed, and we can have a look at the results. And we will, for example, see phase quantities here and some other refined parameters. But obviously this is very old style, and also it's quite tedious to set up the refinement project, to prepare all the files we need. We don't get a visual feedback and no export functionality. So Profex is just a graphical user interface on top of this BGMN kernel. But also, when we run a refinement in Profex, we can still see the same output we previously saw on the command prompt from BGMN. But of course, it's a lot more comfortable to get the visual feedback, to be able to manipulate the graph and add and remove phases to the refinement and all that. But just so you understand that the command running in the background is a separate program called BGMN. And the way BGMN works is it uses text files as input files and generates text files as output files. And the central file everything revolves around is the so-called refinement control file. This is a file we have to create, and it's got the file extension SAV. I call it the SAV file for that reason. And in this file, we reference additional files. So in this file, we configure our project, and we specify which instrument configuration we want to use, or we used to measure the scan, actually. So we give a reference to this instrument configuration file. We also specify which wavelength we used, characteristic wavelength spectrum or wavelength distribution. This is another reference to a file. Then, of course, we have to give a reference to our diffraction pattern and to our structure models, the ones we downloaded yesterday from one of the databases or something that is already bundled with Profex. So in the control file, we reference all these additional files to configure our refinement. And then we call BGMN, or Profex calls BGMN in the background, specifying the refinement control file. And once the refinement is complete, BGMN generates additional output files. And the names of these output files we also specify in the refinement control file. There's first of all the list file that contains the refined parameters, all the refinement results, with the extension LST, and the refined pattern. It's called diagram in BGMN speak, and it's got the extension dia, and a peak list with refined peak parameters. And there may be more. We can generate more output files, but these are the typical files we usually use. So this is what happens in the background. Again, this is an overview of what I just explained, the input files, which extension they have, and what's in the files, what content they contain, and the same for the output files. Now, when we create a refinement project, Profex comes with a set of about 1,000 structure files, and I don't know how many instrument configurations. These are bundled with Profex, and once we create the project, these files, the files we reference in the refinement control file, will be copied from this the bundle location within the Profex program directory to our working directory. So once we have configured a project, we will be working with local copies of these files, and we can modify them, and it will not affect future projects because they will start again with the untouched bundled files. So Profex will copy all these files to the working folder, and then that's where the refinement will take place and where we will modify the files. So yesterday I gave you a short preview how to create a refinement project. Maybe you did it yesterday, or you can try it now. First we open the scan file. Make sure that you see that you set the file format either to the correct file format or to all files, and then open the raw scan. And then we need to identify the phases first, and I showed you different methods yesterday. The double click will be the easiest and fastest usually. So here, if you double click on the two peaks, the strongest peak, it should list apatite and calcite. And then we go to this Add Remove Phase dialog. You can access it with the plus/minus button from the icon bar, the menu bar. And this will open this dialog. And this is where we create our initial refinement project. So if you don't have a project already, this checkbox here at the top left will be checked. So it will generate a default control file. If you already have a project, it will not be checked because this would override everything we have done before. So with a new project, this will be checked, and you have to select the correct instrument configuration from this box to the right, from the list of bundled instruments. And my examples are always measured with this RMS D8 ADS15 instrument. So you have to check this. And then select the phases you want to add. And I recommend to use this filter line here. You can just start typing the name of the phase and it will filter. Otherwise you have to find it among 1,000 structure files. But with the filter it's pretty quick. So calcite and apatite OH are the two phases we want to select, and then click OK. And back in Profex main window you will see that a second tab has been created here with the SAF file and with a fully configured refinement control file. And now we can give it a first try and just run the refinement by clicking the play button at the top, or from the menu Run. You will see that there's also a shortcut F9 that starts the refinement. And once it's complete, as indicated by the green margin around the plot, another tab will open here with the list file. And that's another text file that contains the refined parameters. There's a summary shown down here. Certain parameters will be already shown here, but this is just a summary of what's in the list file, just so we see it more quickly. And of course the refined pattern is shown. Now we have not only the measured pattern, but also the background, the difference curve, the phase contributions, and the HKL tick marks at the top. And on the left, in the plot options list, we now see all these scans listed, not just the measured one as before. So now I want to go back to a live demonstration. Now I want to show you what exactly we find in the refinement control file. So let's have a look at this, at the control file. What do we find here? I will increase it a little bit. So also I would recommend that you go to Window and open the context help. This will open the help module, and when you click on a parameter, it will always show a short description of what this parameter is for. So first of all, you can see different colors. So the text editors use syntax highlighting, and anything starting with a percentage sign is a comment. It's shown in gray, and it's completely ignored by BGMN. So we can add comments as much as we like. It's just for description, that for easier understanding what is in the control file. Then the first variable we see here is called Verzehr, It's a reference to the instrument configuration file. And then lambda is also a reference to this wavelength file for copper radiation. And then we have two structure files referenced here, and they are numbered, number 1 and number 2, calcite and hydroxyapatite. As we add or remove more phases, this will change here. We will add more or remove some phases here. And then with something specific for this RMS instrument configuration is I'm using a measured background scan because I know that my setup will hit the polymer sample holders a little bit. I cannot restrict the beam enough to avoid this. So I'm getting a somewhat wavy background, and it's easier to fit the background if I use a scan of this, of the polymer, of the sample holders on top of the refined background. So this is a scan specifically for my instrument. And then RU specifies for the polynomial background that is also refined, how many coefficients are used for this polynomial. So if we don't specify this, it will just select it automatically. And then the val line, this is a reference to my measured scan. And you may notice that I opened a Bruker specific file format. I think I chose the BRML file format, but here it says XY. That is because BGMN, the kernel, does not support these modern file formats. It only supports a handful of rather old, outdated file formats or the text format. But BGMN will take, not BGMN, Profex will take care of this. So you can load the BRML file or the raw file or XRDML, and Profex will convert it to XY and feed this to BGMN. So this is not something we have to be worried about. And then these are two parameters, Wmin and Wmax, we will use sometimes, or actually quite often. They restrict the range of the angular range we want to refine. So Wmin is the minimum angle where our refinement starts, and max would be the upper end of the range, but this is deactivated by adding a comment sign. So in this case, I started the measurement at either 4 or 5 degrees, I don't remember, but I realized that there are no peaks below 10 degrees. So I just clip everything below 10 degrees to speed up the refinement. That's why it's set to minimum angle to 10. So I can change this at any time if I realize, oh, there's still some information before 10 degrees, I can change it and repeat the refinement. Same for the maximum angle, but normally we want to use as much data as possible. So only if I have a good reason to limit the upper end, I will activate this. And to activate it, I will just remove the comment sign, and then it will become colored as an active line or back to the comment sign. If you right-click on this line, there's a context menu, and you can also choose uncomment or right-click and comment line. It's a bit quicker than doing it by hand. And then we see a number of output file names for the list file, the peak list, and the diagram. This is set up by Profex automatically. We don't have to touch this. So this is where we define the file names of the output files. And then these three parameters, EPS1, EPS2, and EPS3, are fairly important. If you look at the help text, maybe I can increase this. EPS2 refines the sample height error. So if we have if the sample is not perfectly centered, what we discussed yesterday, this will cause a slight peak shift. And we can refine this. And the parameter we use to refine it is EPS2. That's what is described here. EPS1 would be a zero shift. That's just a linear shift of the pattern, not caused by a sample height error, but by a misalignment of the instrument. And this is rarely something that occurs very rarely nowadays with modern instruments. They have digital encoders, so this is not something that we usually need. And then EPS 3 would be a peak shift due to sample transparency. Also something we discussed yesterday, when the radiation penetrates into the sample, we will see a slight shift of the peaks because we get signal from displaced areas of the sample. And then further down, these are two parameters I added myself. These are not official BGMN parameters, I will skip them. N threads is the number of threads BGMN uses for parallel processing. This may be different on your computer depending on the CPU you are using. So it automatically determines how many threads it can use to speed up the refinement as much as possible. Then protocol and save, you can read the text. No, actually there's no help for save. Protocol, it's just whether or not you want to see the refinement protocol while it is running. But I suggest you keep it you leave it at yes, because otherwise you would not see any progress. Also the screen would not update. And save, also leave it at no. Otherwise it would modify this file after the refinement, and we don't want that. Then this whole part down here is for the phase normalization, so the normalization of phase quantities. The scale factor for calcite and hydroxyapatite have this name, calcite and hydroxyapatite. We will learn later how to give these names. And what I'm doing here is just a normalization to 1. So this is just the scale factor, and I normalize them to the sum. So I divide them by the sum of all phases, and this gives my phase quantities: Q calcite, Q hydroxyapatite, and then these are instructions to print to save the quantities to the results file. So this is also automatically managed. If I would like to add another phase, we can try, what should we try? To test for quartz, for example. So I can go here, add another phase. Let's pick one of the quartzes. Just to show how this file is automatically managed. So now Profex added a third structure. It copied the quartz structure file to our working directory. All the rest is unchanged except for here. Now the normalization is changed automatically. And if I remove quartz again, I will delete the file because we don't need it. It's gone. Also, this is set back to only these two phases. So this is what we find in the refinement control file. And if you right-click on these parameters here, you will see different context menus. This part down here, after the last separator line, is context sensitive. So it's different actions depending on where we click. For example, here on the lambda, we can actually select a different wavelength. I could set it to iron, or of course I have to make sure that it's what I actually used. So copper. If I click on a structure file, I can choose to open this file as a text file. So now it opens my structure file. Or what else do we have? Here I could increase or decrease this value. So now it's at 10 degrees. If I can go to 9. And also there's shortcuts, F4 and F6, F5 and F6. So with these shortcuts, I can very easily just modify this as I like. So here, these are EPS 1, 2, and 3 are in this file the only parameters we actually refine. Everything else is just a reference to something. So here I can also choose refine or fix this parameter. So now it's fixed. I can set it to refine, And I will come back to the syntax, what exactly happens here later on when we discuss the structure files. But with the mouse and this help, it should be relatively easy, hopefully, to navigate these structure files and to modify them to your own needs. So that is all I wanted to show for the refinement control files. Now, most of the customizations to the project we do will happen in the structure files. And to open structure files, we can either select this, open file as text, or there's a shortcut Control T, or what I usually use, there's this button up here, the diamond button. It opens all structure files at once. So if I click this, both calcite and apatite will open. This one is just for closing all the structure files. So open, close structure files. Now here, the help also works. I can click somewhere and it will show me the help. And I also want to go through this quickly. If you are familiar with CIF files, you will recognize all the information again in this file. It's just a different format, but it's also a complete description of the crystal structure, just in a different format specific to BGMN. And so it looks a bit different, but it's the same information. We first give a phase name. This name is rather important. It will be used by Profex for different visualizations. And here, for some reason, don't ask me why, but for some reason the comment sign is a double slash and not the percentage sign. That was a decision by the BGMN developer. So just so you know, this is the comment sign here. It's not the same as in the control file. And this is the database record number. So this is a file coming from the PDF4 database, as I can see from this 2, 3, 4 digit scheme. And this is something Profex adds automatically when we import structure files. And even though it's just a comment, Profex will actually read it. And if we go to this dialog, here you can see it will show this comment behind the phase line. So whether or not you are interested in that is up to you. Just so you know that this is, even though it's a comment, it's always there and it will be read by Profex in some places. Then the mineral name, I don't think this is an official BGMN variable. I just added this because sometimes they use fancy chemical names for the phase name, and it's not obvious which mineral phase this is. So we can add additional information. If BGMN doesn't know the variable name, it will just ignore it. That's what is happening with the mineral name. These trailing comment signs, there was a historic reason on some very old systems that the BGMN developers decided to add these, but they are not needed. We can remove them. It will work anyway. So these just mark the end of the lines for some reason. But you can also leave them in, doesn't matter. The formula is just for description purposes, and then we have the space group, the number from the international tables. This is important, and then the Hermann-Mogin symbol. This is not the same notation as used by CIF files and probably some other sources, so it always depends, do they use the short or the full notation of the symbol, and do they add spaces between the different positions or not. So usually, if this is correct, you don't have to touch it anymore. Also the number, this is not something we refine, so it's just there. Then on the next line, these are the cell parameters A and C. In a triclinic structure, we would also see additional parameters, of course, B and alpha, beta, gamma. In a hexagonal structure, as the calcite is. We don't need this. So because these are given, alpha, beta are 90, gamma is 120, and the B-axis is the same as the A-axis. So we only list the ones that actually can be refined, that are not fixed by the symmetry. In this case, A and C. The next line is the most important line, actually, the one we use the most. It's the profile refinement. So the peak shape refinement. And the first parameter, RP, is just an instruction. It can be set either to 2, 3, or 4. These are the acceptable values. And 2 means that we do not refine any peak broadening. 3 means we only refine crystallite size related peak broadening. And 4 means we can refine microstrain and crystallite size peak broadening. This is described here in the 2, 3, and 4. The default should be 4 in almost all structure files. So usually we don't change this. And then we have 4 parameters, K1, K2, B1, and Gewicht. And these are extremely important. Not in this order, actually in the reverse order, starting at the end. Gewicht is the scale factor, but it is already corrected for the unit cell density. This means that the Gewicht parameter, even though it's a scale parameter, a scale factor, it's proportional to the phase quantity. We don't have to apply any additional corrections. And that is also why in the structure file we can simply normalize here these parameters, just divide by the sum and we will get the quantities, because all these corrections are baked in to this Gewicht parameter. But it is the scale parameter, the scale factor, and it is also, as we will see later, where we refine texture. But I will come back to this later. So Gewicht is very, very important. Then the B1 parameter is the refinement of peak broadening due to small crystallites. There's a bit more explanation here, but if we refine B1, we will be able to refine the crystallite size. K2 is peak broadening due to microstrain. If we refine it, we will refine microstrain. And K1 is refinement of the crystallite size distribution. These we will use a lot in the examples we will do later on today. Usually the first thing, if we don't get a good fit, we check, do we need different peak width refinement? So we will address the B1 and the K2 parameters. Then these 2 goal statements I will explain in more detail later on. I will skip this for now. And then at the bottom we have lines, 1 line for each atomic position. And it starts with E equals, I assume this means element, and then we specify the scattering factor, so the element for this, this phase. And we give the symmetry of this site by specifying the Wyckoff symbol. This is not refinable, it's just something that we take from the database. And then there's the 3 fractional coordinates, x, y, z, and a thermal displacement parameter. So the vibration of this site. How the unit, if you are familiar with other software for Rietveld refinement, they usually use 100 times higher values here. It's because BGMN always calculates in nanometers and not in angstrom. So the unit of this is actually nanometers squared, whereas other software uses angstrom squared, and then you have to multiply the same number with 100. So just if you wonder why these numbers are so small. The Wyckoff position B is not a general position. It's actually fixed at the origin of the unit cell at 0, 0, 0. So this means that if we declare this calcium position as Wyckoff B, we cannot refine the fractional coordinates because B means it's in the origin. And we could also just delete this. B is enough, Wyckoff B is enough to tell the program that it's in the origin. Here, Wyckoff E means that it's located at Y0 and Z 1/4, but X is a general coordinate, so X can be refined. So let me undo this. So just so you know that you may, I don't know if it gives an error message or if it will just ignore it if we try to refine this parameter that we are not supposed to refine. We can test it later on, I don't know. One thing I noticed here, there's actually a bug in this file. It does something we should not do. It mixes an ionic scattering factor with atomic neutral ones. This is illegal, but the software will not complain. So what it means that we are not using, we actually don't have enough electrons in this structure, because these are neutral ones and this one is positively charged. So we have to use either all charged ones or all neutral ones. Otherwise there's a problem. So in this case, I can just delete this. Let's check the appetite. Here it's okay. Here we only have neutral ones. So in these files, we determine which parameters we want to refine and how we want to refine them. And again, the context menu of the mouse cursor can help us a lot. So if I place my mouse or the cursor on the A parameter, I right click, and then I can choose to refine it isotropically, anisotropically, or fix it, not refine it. And if I do that, the code will change. So now the A and C parameters of appetite will not be refined. They will be fixed at their published values. If I choose to refine them isotropically, anisotropically doesn't work for all parameters. So it will add some code automatically to refine the parameters, to set them as a variable. This is how we choose what we want to refine. So usually the axis parameter, so the unit cell axis we want to refine. This is one of the first parameters we want to refine. And now we have to decide how can we improve our fit. So if we go back to the refinement, we are still stuck here. Yesterday I spent a lot of time explaining or mentioning that you have to understand so what we see in the diffraction pattern, how is this related to the crystal structure? And this is exactly what's important now. Now we see that the refinement of this data set is okay-ish, but it's not perfect, especially the strong calcite peak here. If we look at this, there's something wrong with the peak shape. And now we have to understand, so what do we change in the structure files to improve this fit? And if you remember peak width, that was two sources in the crystal structure that changed the width of refinement of XRD peaks. It's a crystallite size that causes peak broadening when the crystallites become small in the nano range, and microstrain. So dislocations, substitutions, vacancies, things like that. So we have to somehow improve the refinement of crystallite size and or microstrain of calcite to fix this misfit. So we go to the calcite structure and check how is it refined at the moment. Remember, B1 is the refinement of the crystallite size, or the peak broadening resulting from crystallite size, to be correct. And this is already refined. As we can see, when we fix it, it will be just fixed at 0, or when we refine it isotropically, it will be parameterized by this keyword. So this is already refined, but K2 is the parameter that describes peak broadening from microstrain, and this is not refined. So we can just guess, maybe the fit becomes better if we refine microstrain. So we set this to refine isotropically. And then we just give it a try. Run the refinement and see what happens. And indeed, the fit looks a lot better. I forgot to check the chi-square parameter here, the goodness of, so it's a description for goodness of fit. I forgot to take note of this before I started the refinement, but it should be a lot lower now. It was probably more than 2, certainly. So the smaller this value gets, the better the fit is. So now we refined this microstrain parameter, and in the list file, which contains all our refinement results, we can scroll down. So first of all, here we can see the phase quantities. Calcite was refined to 47% and hydroxyapatite to 52.6. And then we have the refined calcite parameters. This is the A parameter, the C. And we have some very small number for the microstrain. The crystallite size, so the peak broadening parameter, was refined to another small number, and it calculates the actual crystallite size from this B1 parameter, and the crystallite size of calcite was calculated to be 183.9 nanometers. So the fit was already improved a lot. We will continue working on this data set in the afternoon. But before that, I will have to show you some more information about the structure files, what we can do with them. So that was just a very basic introduction, how to release one parameter, this K2 parameter, for refinement. And in the next lesson, we will dive more deeply into the structure files. I will show you how we can refine things like substitutions. And we will do this with this data set. And then we will also talk about how to create our own instrument configuration files.